Okay, the purpose of this video is to discuss stability in the context of a dynamic system. And in particular, there are several different types of stability that you can look at. In our case, we're going to look at what's called BIBO, B-I-B-O, which stands for Bounded Input, Bounded Output Stability. And the idea behind it is this. If I have a system that has an input x of t and an output y of t, this system will be BIBO stable if I can say that the absolute value of the input being less than some constant a for all t, if this implies that the absolute value of the output will be less than b for all t. So if this statement implies that this statement is true, then the system is bounded input, bounded output stable. Conceptually, what this means is that as long as the input does not get to be too large, so as long as this stays bounded, then the output stays bounded, and the idea is that that usually means that the system's stable. Well, that means that the system does what you want it to do, or at least doesn't do what you don't want it to do. So let's do a few simple examples of systems and try to determine if they're BIBO stable. So suppose we have a system where what the system does is multiply the input by a gain so that y of t is equal to some gain times x of t. And the question is this a bounded input, bounded output stable system? Okay, well, the idea, or we have to check that if this is true, that is, if x of t, the magnitude of x of t, or the absolute value of x of t is less than a, then will the absolute value of y of t be less than b? A here is something that we can tell basically from the signal. So for example, if I talk about a unit step function where the unit step function looks something like this, it's 0. It's 0 for values of t less than 0, and it's 1 for values of t greater than 0. Then say I pick a equals 2. Well, if a is equal to 2, then clearly the absolute value of u of t is either 0 when t is less than 0 or 1 when t is greater than or equal to 0. So I could pick a value of a is equal to 2, and this inequality here would be satisfied. Okay, so let's assume that we have some arbitrary input x of t where this inequality is satisfied for some value of a. Now if I look at the output, the absolute value of y of t is the absolute value of the gain times x of t, and this is the absolute value of the gain times the absolute value of x of t, and this is less than the absolute value of the gain times a of t, because again we're assuming that x of t satisfies this inequality. And so if we take then b as defined by the absolute value of the gain times a, then the output of this system satisfies this inequality. Okay, so a gain is a BIBO stable system in the sense that anytime I put a bounded signal in, I get a bounded signal out. Okay, now it is possible to have an unbounded signal, for example, well, u of t is a bounded signal. If I had e to the at, as t gets large, this thing gets large too. And so this e to the at does not satisfy this inequality here. Okay. So let's look at another example. First, let's tidy up a bit. Get rid of all this clutter. In fact, we'll get rid of all of this. So we have lots of room for this next system because it could get a little hairy.